In the last lecture, we derived an equation called the Born-Meyer equation, which we can use for calculating the lattice energy of ionic compounds. Let's revisit what the Born-Meyer equation looks like. There's really two parts to the Born-Meyer equation. All of that stuff in front of the parentheses, that is giving the electrostatic potential energy of a lattice of point charges. And then we've got this term minus rho over d naught, which is a term that we added to take into account the repulsions of ions when they get too close together. Now let's walk through an example where we use the Born-Meyer equation to calculate the lattice energy of an ionic compound. The example we're going to do here is potassium chloride, which has the rock salt structure. Now if we were to look at this equation, really all of the things we have to put into the equation are readily available, and the one thing that is not so clear would be, what do we use for d naught? That's the equilibrium distance between the center of the cation to the center of the anion. And so to get that distance, we're going to estimate that from ionic radii. The best set of ionic radii are called the Shannon radii, or sometimes they're called the Shannon-Pruitt radii, because the original set was developed by two scientists, Robert Shannon and Charlie Pruitt, and then later revised by Shannon. If we look at those radii, and here's a link to one place you can find them, then we would see that the radius for potassium cation is 138 picometers, and the radius of a chloride anion is 181 picometers. So when we add them together, we get this equilibrium bond distance of 319 picometers. I might point out that the Shannon radii vary by the coordination number. So here, I've chosen the radii for 6-coordinate potassium and 6-coordinate chloride, which is the correct coordination number in the rock salt structure. To the extent that we can do it, we're generally going to try and use radii with the most accurate cation coordination numbers. So now I'm in a position where I can plug all of the variables into my Born-Meyer equation. One for the charge on the potassium, one for the charge on the chloride. Here I'm just using their absolute positive values. We've got a negative sign in front that takes into account that we're always multiplying the charge of a cation and anion together, so that's always going to give us a negative charge. In SI units, when we say something has a charge of +1 or -1, what we really mean is +1 or -1 times the elementary charge of an electron, which is given here 1.602 times 10 to the minus 19 coulomb. So there's that quantity squared. We're going to multiply by Avogadro's number. Going to divide by 4 pi. This is the electric constant, or the permittivity of free space. And then here is our equilibrium distance, 319 picometers. Remember that a picometer is 10 to the minus 12 meters. 1.748, that's our Madelung constant for the sodium chloride or rock salt structure. And then here we're going to take rho as a kind of an empirical constant that's 34.5 picometers, divide by our equilibrium bond distance. So when you put all of that into the calculator, you're going to get minus 679 kilojoules. You can see that if we didn't have the repulsive term, it would be minus 761 kilojoules. So the inclusion of the repulsive term reduces the lattice energy by, ballpark of about 10%. Now, we might ask ourselves, how close is that to the true lattice energy? That takes us to something called the Born-Haber cycle, which probably you've seen before. And the Born-Haber cycle is a method of obtaining an experimental value for the lattice energy. All right, so the idea in a Born-Haber cycle is we start from potassium metal and half a mole of chlorine gas. Of course, we could let those react and measure the enthalpy released. And if you did that, you would find that's 436 kilojoules per mole. Potassium chloride is more stable than elemental potassium and elemental chlorine by that amount. But we could come around it in the opposite way, where we first vaporize the potassium, That costs us 90 kilojoules per mole. Then we split the chlorine molecules up into chlorine atoms. And that costs us 122 kilojoules per mole. Then we ionize the potassium atoms to potassium ions, and that's kind of expensive in terms of energy. That costs 419 kilojoules per mole. And then we allow that electron to attach to the chlorine atom, making chloride ions, right? And that's just the negative of the electron affinity of chlorine. Here we're calling that the electron gain enthalpy. We finally encountered an exothermic term. Now that we have potassium ions and chloride ions in the gas phase, we can let them come together to form potassium chloride. Right? By definition, that is the lattice energy, is 718 kilojoules per mole. So that is our lattice enthalpy. And remember from the last lecture, we said there's very little difference between lattice enthalpy and lattice energy. So we're going to take that as a proxy of the lattice energy. Before we leave the Born-Haber cycle, there is one thing that I think is always kind of interesting to look at. Now, we would normally, as chemists, say, oh, it's very favorable that a potassium atom would readily give up its electron to a chlorine atom to form ions. Right? But notice here that that is actually uphill in energy to go from potassium and chlorine atoms in the gas phase to potassium and chlorine ions in the gas phase. However, we do know that potassium and chlorine react very exothermically, right? And that does trigger this transfer of electrons. But the thing to realize is the exothermicity of that reaction is driven largely by the favorable lattice energy that comes from the attractions between potassium ions and chloride ions. Now, back to the question of how accurate was the Born-Meyer equation. Well, remember in the Born-Meyer equation, we got something like minus 680 kilojoules per mole. Here we see the true lattice energy is more like minus 718 kilojoules per mole. So the Born-Meyer equation underestimated the lattice energy by a little bit. It was maybe on the order of 5% too small. But, you know, for such a simple-minded approximation as treating all of the ions as point charges, that's not too bad. Here we can see for all of the alkali metal halides that take the rock salt structure, the curve is the lattice energy that would be calculated by the Born-Meyer equation, right? And the only variable there is going to be the interatomic distance. So we can plot that for any given interatomic distance. The symbols show the experimental lattice energies that we get from a Born-Haber cycle. You can see that the Born-Meyer equation does a pretty good job of capturing the variation in lattice energy as the interatomic distance changes, but it does tend to underestimate the lattice energy by somewhere between about 3 to 6%, depending on the compound. Now, it is possible with these kinds of relatively simple calculations that we can add a couple more terms to take into account factors that we know we're neglecting. So up to this point, we've basically just used these first two terms, right? The Coulomb energy, right? So that's basically just the interaction between these ions, and that gives us a negative number, and that's the major part of the energy that comes out of this expression. Then we had added in the repulsive interaction, right? And that's depends on the compound, but it should be somewhere between maybe, here I'm saying 9 to 17% of the Coulomb energy. We could, if we wanted to be even a little bit more accurate, add in a term here with a 1 over distance to the 6th dependence, right? That's going to be like your van der Waals forces or your dispersion forces between ions. And that makes the lattice energy more negative, more stable, by, let's say, 1 to 5%. And then we have one final term, which is the 0-point energy. And the 0-point energy comes from a quantum mechanical term that I don't want to get into here, but that is the opposite sign of the dispersion forces, right? So that makes the lattice energy a little bit more positive. We oftentimes will neglect these last two terms because they're pretty small And because they're opposite sign, they can kind of almost cancel out. Now, let's think about a family of compounds and everything that we've learned about ionic bonding up to this point, and then think about what sorts of structures we would predict to be the most stable. Here we're going to look at 6 different cations and 4 different halide anions that together form these MX2 structures. With this stoichiometry, we've got the fluorite structure, which is shown here, where the cation has 8 anion neighbors and the anion has 4 cation neighbors. We talked about the rutile structure, where the coordination numbers go down to 6 for the cation and 3 for the anion. We also have some of these layered structures, like cadmium iodide and cadmium chloride, which basically only differ from each other in the way the layers stack. But in these structures, we're only filling half of the octahedral holes, and the way that we're filling them is such that we have layers where all of the octahedral holes are filled, and then layers where the octahedral holes are empty. Now, if you look at the Madelung constants below, we can see that the fluorite structure, having the largest coordination number and also a very symmetric distribution of cations within the octahedral holes, it has the largest Madelung constant. So naively, we would say the fluorite structure should win out. And we can see in the lower left part of this table, when we have large cations and relatively electronegative halide ions, that the fluorite structure is what's observed experimentally. But there's a couple of trends here that suggest there's more to it than just the value of the Madelung constant. We can see for the fluorides that as the cation gets smaller, the rutile structure emerges as the most stable structure. As we go to larger, less electronegative halide ions, these layered cadmium iodide, cadmium chloride structure emerges as the most stable. I don't want to get too much into the lead chloride or the strontium iodide structures because they're not quite as symmetric. They're a little bit more complicated to draw. But maybe the thing you might want to remember about those structures is that the cation coordination number is a 7 in those structures. So what's going on here? What explains these trends? Why don't you just pause the video for a second and have a little discussion if you're in a group, or maybe if you're watching this by yourself, just jot down some ideas of what's going on here. What causes these structures to emerge as the most stable in different parts of this table? Let's take a look first at the size argument. So let's concentrate on the fluoride compositions in this table, and we see that for small cations we have the rutile structure, for large cations we have the fluoride structure. Here I'm going to show a graph from what now is kind of an old paper by Mark Wilson and Paul Madden. And what they've done here is they've done calculations that are similar in spirit to the Born-Meyer equation. They've got a somewhat more sophisticated way of treating the repulsive interactions between ions, and I think they also added maybe in some dispersion forces. But it does allow them to make predictions of lattice energy as we change the radius of the cations. What we see is for small cations, the rutile structure has the most negative energy. It is the most stable. But then, as the cations get larger, there's a crossover point here where the fluorite structure becomes the most stable. So even in these relatively simple calculations, not much more sophisticated than the Born-Meyer equation, we can predict that there will be a crossover from rutile to fluoride as the cations get larger. We notice that these layered structures are always significantly higher in energy. And it's not hard to imagine the reason for that, because all of them have the same number of cations per anion, right? Half as many cations as the anions. But in the cadmium iodide structure, we have put all of the cations into layers. So we have not maximized the separations of the cations. And those shorter cation-cation distances are going to lead to more repulsive interactions that lead to a less negative lattice energy. So let's take just a little closer look at why the rutile structure, even in these Born-Meyer equation, kind of emerges as the most stable structure when the cation radius gets small. Now, before we do that, we have to take a little aside and talk about values of ionic radii. So if you were to go back into the Shannon and Pruitt paper and then the later Shannon paper from '76 and look at their radii, you would see that there's two sets of radii. They have a set of radii they call the ionic radii, and then they have another set of radii they call the crystal radii. When we talk about the ionic radius of a strontium 2+ ion, so what's known experimentally to a high degree of accuracy is the distance between the center of a strontium ion and the center of the anions that are around it. Let's say here fluoride. So they looked at all of the compounds containing strontium and fluorine. They looked at that distance from the center of one ion to the center of the other ion, and then they took an average and they said, well, okay, let's divide that further into some of it coming from the fluoride and some from the strontium. So in the ionic radii, they chose the radius of the oxide ion and the fluoride ion to match the original ionic radii proposed by Linus Pauling. So those were the values that were well accepted, and they said, okay, let's go with those same values. Because experimentally, it's not very easy to measure exactly where the fluoride ion stops and the strontium ion begins. But that's not to say it's impossible. And if you do careful crystallographic work, you can see where the electron density of one ion might end and the other ion begins. And if you do that, you come to the conclusion that Pauling thought the anions were actually larger than they really are. Shannon and Pruitt, their estimate is that these anions are actually 14 picometers smaller than Pauling estimated. So if you were to look at the crystal radii, the sum of the anion plus the cation is going to be the same, whether you use the ionic radii or the crystal radii. But in the crystal radii, all of the anions are 14 picometers smaller, and all of the cations are 14 picometers larger. Now, why am I even bothering to tell you all of this? There was a point in time when I was a big proponent of using crystal radii because they just seem more accurate. But most of the world seems to want to stick with the ionic radii, and I've kind of more or less conceded that that's what we're going to do. But in what follows, we're going to talk about these ions as though they really were hard spheres, and we want to look at where the anions start to overlap. And in that kind of consideration, it's best to use the crystal radii. So we're going to use the crystal radii for the rest of this lecture. Now, if we were to take a cation and put it into a cube of anions, as I show here, as you have in the fluoride structure, there's a couple of distances we can get from simple trigonometry. So the distance from the center of the cation to the center of the anion, here d1. If we make the cation magnesium and the anion fluoride, that distance is just 205 picometers. And we can get it simply by adding the radii of the two species. Now, because it's a cube, once we've specified this distance, we've also fixed the distance from the center of the fluoride ion to the center of the neighboring fluoride ion. If we take 2 times this d1, that is the cation-anion distance, 2 times that would be the body diagonal of this cube. And then if we divide by the square root of 3, we get the edge length of the cube, and that's the fluorine-fluorine distance. So when you do that, you come up with an estimate of 237 picometers from the center of this fluoride ion to the center of this one. Well, how does that compare to the actual radius of a fluoride ion? Well, the radius of a fluoride ion, 119 picometers, we multiply that by 2, and we get 238 picometers. So what we see is that the size of the magnesium cation is such that to get the optimal cation-anion distance so they touch, we practically have to bring the fluoride ions together so they touch. And that second thing is not favorable, because as the fluorides get close to each other, we get these repulsions between the core electrons. So it starts to become unfavorable to put 8 anions around the cation when the cation gets too small. If we were to reduce the coordination number to 6, like it is in rutile, here I'm just looking at, let's say, the equatorial plane of an octahedron. So if we wanted the full octahedron, we'd have one anion above and below. I'm not drawing those just so we can see the geometry. Now, what is the anion-anion distance? Well, a little trigonometry here again. We've got a 45-degree triangle, and so the side of the 45-degree triangle is just the d1 times the sine of 45. And if we take that distance and then multiply by 2, then we'll have the fluoride-fluoride distance. And we come up with 290 picometers. Well, 290 picometers is considerably larger than 238. So now we see the anions are not close to touching. We don't have these unfavorable repulsions between the core electrons on the fluoride ions. So that's basically what drives going to smaller coordination number as the size of the cation gets smaller, or as the size of the anion gets larger. Now, eventually, even 6-coordinate becomes too small, and we can do the same calculation for zinc sulfide. What we get is the zinc-sulfur distance being 281 picometers, and then the sulfur-sulfur distance being 397 picometers, and that 397 is very close to the sum of 2 sulfide ion radii. So now the sulfur ions are practically touching. We're getting unfavorable electron-electron repulsions between the sulfurs. And if you know anything about the crystal chemistry of zinc sulfide, you know that the structures it adopts, wurtzite and zinc blende, both have 4-coordinate zinc rather than 6-coordinate zinc. A long time ago, in the early part of the 20th century, Linus Pauling said, all right, we can just take the ratio of the size of the cation and divide by the size of the anion. And with that geometry that I just walked you through, you come up with the conclusion that when this ratio, rho, is bigger than 0.7, we could fit 8 anions around the central cation. When it dips below 0.7, it's not possible to fit 8 anions around the cation anymore, and the coordination number drops to 6. And when the radius ratio drops below 0.4, then we can't even fit 6 around it, and the radius ratio predicts that the coordination number is going to drop to 4. All right, let's go back to our table here once again. Remember, the green ones have coordination number 8. The blue and the red are coordination number 6. And then these white entries over here, that would be coordination number 7. So what kind of radius ratio do we get for these compounds? So if we use these crystal radii, which are more accurate than what Pauling knew, we come up with these sorts of numbers. And I guess the thing I want to stress is that there isn't really this hard cutoff. 0.7 is not really a magical number because these are not perfectly hard spheres. But there is a trend that as the radius ratio gets smaller, the coordination number of the central ion also gets smaller. Here in the fluorides, below about 0.96, we have a crossover from 8-coordinate to 6-coordinate for the cations. In the chlorides, which are a little bit softer, that crossover is somewhere between 0.79 and 0.68, and so forth and so on. So don't take the radius ratio as a magical thing, but there is a logic to the cation coordination number getting smaller as the radius ratio gets smaller. Now, this still does not tell us anything about why these entries over here in red, zinc chloride, zinc bromide, manganese iodide, why don't those take the rutile structure? I mean, it's 6-coordinate in both. We have a considerably larger Madelung constant for rutile than we do for cadmium iodide. Now, if we go back to these calculations of Wilson and Madden, remember that this also predicted that we should never see the cadmium iodide structure. But we do. And in fact, layered compounds are a really topical area of research in the modern day and age. So what's responsible for stabilizing these layered structures? In the same paper, what they did is they introduced another term that added a little bit more sophistication to the modeling. And what they allowed to happen was they allowed the electron cloud around the anion to deform. In other words, think about it as a polarization. So if you have like a big iodide ion and its negative charge is distributed over this rather large spherical electron cloud, and now on one side of it we put, let's say, a small cation like a magnesium. Well, you're going to create an induced dipole. The electron cloud is going to shift toward the cation, and so we will now no longer have a symmetric electron distribution. And when you just allow that one thing to come into the calculation, now we see that the cadmium iodide layered structure emerges as being the most stable structure when the cation radius gets small. At least here for the bromides, which are kind of a middle point of our series there. Okay, so allowing this induced dipole, you can kind of see where that might lead to an improvement in the lattice energy. I mean, I should say, if we were to go back to the old calculation, what's happened here is the layered structure, its Madelung energy or lattice energy has come down a lot. The fluorite structure basically hasn't changed, and the rutile structure has changed downward just ever so slightly. So why is the effect so much larger for these layered cadmium iodide, cadmium chloride structures? And to answer that question, we need to look at the anion environment and think about the kind of polarization effects you're going to get when you put cation charges in different arrangements around the anion. So in the fluorite structure, the chloride ion is surrounded by a tetrahedron of cations. It's a perfect tetrahedron. So you can think about each of those cations pulling the electron density toward it. But because it's so symmetric, the way they pull on the electron density exactly cancels out. And so we don't get any kind of a dipole at all for the chloride because of the symmetry of its environment. If we go to the rutile structure, now we have something that's close to, but not quite, trigonal planar. If it was perfect trigonal planar, the same thing would happen. This cation would be pulling the electron density in this way, this cation in this direction, this cation in that direction, and they would all cancel out. In the rutile structure, the actual site symmetry is C2V, 2 mm. This angle is not quite 120, it's smaller than 120, and there's just a very, very small polarization can then occur. But if we go to cadmium iodide, and we've got this trigonal pyramidal geometry, well, now all of the cations are on the same side. They're all trying to pull the electron density downward, and that environment is actually quite favorable for creating this kind of dipole moment on the iodide ion that I show here. Okay, so we get significant anion polarization in these layered structures with asymmetric anion environments, and no anion polarization in these very symmetric structures like fluorite. And that's basically the reason why we get such a stabilization of these layered structures. Now, the other thing that's beneficial about this induced dipole is by pulling the negative charge of the anion down toward the layers that contain the cations, we also reduce the repulsive interaction between anions across this empty layer. Okay, and that's also important in stabilizing the structure. And these effects get increasingly important as the anion becomes larger and more polarizable. So the fluoride ion is not so readily polarized. Chloride is more polarizable, and then of course bromide and iodide are actually very polarizable anions. And so they tend to favor these asymmetric coordinations by cations that allow the electron density to be polarized. And at the end of the day, that's the reason why we see these layered structures for the heavier halides.